Good morning. Today I will discuss tutorial on ANOVA. We have two tutorials today. One is tutorial 1 for one-way ANOVA and two-way ANOVA. Let us see the tutorial first one-way ANOVA. The problem is, in order to evaluate safety performance of employees across 3 departments, 5 employees across each department were randomly monitored and their safety behavior on a 100-point scale is given below. Do the departments differ in their safety behavior? This is our question. Now, the data points, you see that there are 3 departments A1, A2, A3. Each departments we have collected 5 data points 1 to 5 and these data are 68, 73 like this. Now, we will see the details of one-way ANOVA with respect to this data set. So, if you make the total across A1, the total score on safety behavior is 359, across A2 it is 413 and across A3 it is 368 and the grand total is 1140. So, we are adding little some different notation now. I am saying that AL is the total score or the total values, total of population L, and we are saying G equal to the grand total. This will be definitely L equal to 1 to capital L. Okay. So, what is our ANOVA model here? ANOVA model is XIL equal to mu plus mu L minus mu plus XIL minus mu L, which is mu plus tau L plus epsilon IL. This is our ANOVA model we have seen, and we will now see the computation of AL and G. So, if you what will be the grand total? Grand total will be sum of, I think I have already given you, XIL, I equal to 1 to NL, L equal to 1 to L. This will be the grand mean, and what will be the sum of this? AL, L equal to, so I equal to 1 to NL X IL. And then we have seen what is the computation of SSA, that is sum square total. Here we will use little different computation for ease of computation, that is this one you write down, I equal to 1 to NL, L equal to 1 to capital L, XIL square minus, we are saying that G square by N. Please write down SSA equal to L, small l equal to 1 to capital L, I equal to 1 to NL, XIL square minus G square by N, where G is the grand total. Grand total, and this is our not SSA, this is our SST. This one is SST, sum square total. Now, sum square A means the population, we are defining that population A. This one is now L equal to 1 to capital L, AL square divided by NL minus G square by N. Okay. So, this one, if you see here in this slide, you see what we have written, these are all the earlier values, that these values, the 68, 73, 75 like this, these values are squared. These are all squared values, and this is the squared sum square values across A1, across A2, across A3, and finally this is the grand sum squared values. So, SST calculation formula is L equal to 1 to L, I equal to 1 to N, XIL square minus this. Now, this value is the square sum square of all these values. So, it is 87176 minus G square. G already we have found out. You see what is the value of G? G is 1140. So, 1140 square by N. What will be the value of N? N is L into N, sum of NL into L. So, here in this case our N1 equal to N2 equal to N3 equal to N, and L equal to 3 and N equal to also 5. So, capital N will be 15. So, that is why what is happening here, G square by N, that 1140 square by 15, and this quantity is 536. Now, SSA will be this one, L equal to 1 to capital L, AL square by N. You see what is this AL square? A1 square is 25, 887, A2 square is 34, 171, and third one A3 square, which is 27,118. This sum divided by N, okay, and then minus G square by N, this quantity will be 334. So, then what we have got now, SST equal to 536, SSA equal to 334.80, and SSE equal to SST minus SSA, which is 536 minus 334.80, which is 201.20. Okay. So, we have already seen the ANOVA table for this, sources of variation, then your SS, first is source is here population A, then error, then total, then SSA is our 334.80, SSE is 201.20, and SST is 536. And what is our degrees of freedom? A 3 minus 1 equal to 2, this will be N means 15 minus 1 equal to 14, then this will become 12. Then what is our MS value? 334.80 by 2, 330.80 by 2 will, what will be this value? 330.80 by 2. Okay. So, this is SST is 530, SSA is 330.80 by 2, you write down, then 201 by 12, and then you write down that F statistics. F will be 334.80 by 2 divided by 201 by 12, some value will come, that you have already seen. So, our this one, this total this calculation, if I made, ultimately it will be like this. 334 by 2 means 334.80 by 2 means 162.40 divided by 201 by 12, that will be 1 then 81, that 6 into 8 5 something like this. So, the F will be 162.40 by 16.85. not coming. So, F is 162.40 by 16.85, it will be almost equal to 10. It simply indicates that there is difference in safety behavior across the departments. Okay. So, once that difference is established, what is required to know, we will go for estimation of parameter. Now, you see the this slide, this is what is estimation of parameter. First one is we want to estimate the grand mean, which is the G bar. Grand mean estimate is G bar, that is G by n, and your individual mean estimate is here, it will be your AL bar, which is AL by, I think it is AL by small n, because all cases so we have taken equal sample size. And we are showing here one method which is known as Tukey method or Taki method. So, this Taki method is used to see the difference in mean values, the confidence interval as well as the hypothesis testing, that means whether the difference is statistically significant or not, and if and what is the interval, confidence interval for these differences. In this is simultaneous confidence interval. Please keep in mind that here one statistics is there, Q alpha A n minus L, which is known as studentized range statistics. This Q statistics here, what Taki use is studentized range statistics. So, it is similar to other statistic like Z and chi-square and other, but the values will be different. Here alpha is the probability, A and n minus L, these are the other two parameters which will be used for seeing the table. So, you have to see the studentized range statistic table. Taki statistics is popularly used. Then once you use this, you can go for this interval estimation. For equal sample sizes, it will be like this, and unequal sample sizes, only that 1 by NL plus 1 by NM, this quantity will come into consideration. Now, let us see for the data points what we have discussed here. Our data point is this. These are the data points given. Now, with respect to this, we want to see all the parameters. Here tau L, that is tau 1, tau 2, tau 3. What will be the tau L? Tau L is mu L minus mu. So, if I say tau L estimate is mu L estimate minus mu estimate, what is your tau L value here? A L bar minus G bar. So, we know all those values we know. Now, what is your AL bar? This is AL 359. So, 359, then 413, then 368, and the grand total is 1140. So, here you divide it by 3, 5, you divide it by 5, here you divide it by 5, here you divide it by 5, here you divide it by 15. So, then what will happen, that A1 bar, A2 bar, A3 bar and G bar equal to this. What will be this value? 359. So, it will be 71.80. Second one is 80 point, what will be this value? 8413, 5, this will be 8, 40, 1, 3, then 2, 10, that is 82, 82.60, and this one will be 5 into 7, 35, 5 into 3, then 30, 70, this 0, and this will be 1140, 15. So 15 into, I think it will be 7, 105, then 90, 15 into 6, 76. Now you come to this values here. What will be your this one, that A1 bar is given, G is given, the difference is tau 1. So, what will be my tau 1? Tau 1 will be my A1 bar minus G bar, which is 71.80 minus 76. Is it 4 minus 4.20? Okay. So, similarly tau 2 bar will be 82.60 minus 76, 6.60, and tau 3 bar will be 73.60 minus 76, so minus 2.40, and the sum total will be 0. Then what we want? We want to calculate also the error terms. What we have seen? We have seen that XIL equal to your mu plus mu L minus mu plus XIL minus mu L, what is nothing but G bar plus AL bar minus G bar plus XIL bar minus, this is mu L, so AL bar. So that means this one is our epsilon IL. So epsilon IL is each of the values minus AL bar. Now see, you have already computed AL bar. AL bar is 71.80 for A1, for A2 it is 82.6, and A3 for this bar values are there. So you go back to the original table again. Now 68 across A1, 68 minus, what is my G bar? G bar is 70, 68, what you require to do? 68 minus AL bar, this is the value. So what is your AL bar? Achha, I am just taking only few. First one from the first this column only I am taking. So 80. So this one will be A1 bar, this minus A2 bar, then 73 minus A3 bar. So this sense you have to make. Now again go to this our what is where we have calculated G bar, AL bar, A1 AL bar is 71.80. So 68 minus 71.80. What will be this value? Is it not minus 3.80? Then 85 minus 82.60, is it not 2.40? Then 73 minus our 73.60, this is minus 0.60. So what I mean to say here then? I mean to say that for each of the observations you have already in one table. Now the mean of A1 bar, that is A1 bar, A2 bar, A3 bar you have computed. You subtract each of the cell across A1 by A1 bar. Similarly, A2 cells by A2 bar, A3 cells by A3 bar, whatever you will get, that is the error quantity. Correct. So once you know the error, you have to go for certain adequacy test as well as your normality test and other tests are there. Suppose I want to do the normality test. This is known as model adequacy test. What way you will do normality test? How do you go about it? Because you have to do it from the errors. So first step is arrange the errors in ascending order. Okay. So, suppose in this case what you have 1 2 like this the 15 data points, and then your errors are coming something like this IL, but you are arranging them in ascending order. So, you will be getting some values. When you arrange here, you will be getting minus 6.80, minus 4.60 like this, 3.4, 6.2 like this you will be getting. Okay. Then what you require to do, you have to find out the probability value using this, that is empirical probability value using I. What is required to be written here? 100 into I minus 0.5 by your n. 100 into I minus 0.5 by n. So, it is 100 into 1 minus 0.5 by 15, 100 2 minus 0.5 by 15. In this manner, you will be writing 100 last one into 15 minus 0.5 by 15. What value you will get? This value you will be getting. So, first one 100 I minus 0.5 by n is 3.33. So, you must have E values, that error values. You arrange them in ascending order. You have number of observations, in serially it is arranged. So, now you are calculating this. So, this is one of the way of finding out the probability value, this in terms of percentage, and then you plot. What is the plot? Plot is percent probability and then residual values, these values. So, your first residual is your minus 6.8, probability value is 3.33 something, it is coming somewhere here. So, once you get like this, then you draw a straight line. If you get a good straight line, in that sense the different error points will not differ much from the straight line, we can say that normality assumption is valid. Okay. Now, you may not be interested to use this 100 into I minus 0.5 by n, you may go for some other formulation is there, different people have different, but this is widely used one, we are using this. Okay. So, this is the first what I can say the adequacy test. So, please keep in mind what way we are proceeding. We have data, you have to first test hypothesis using the one way ANOVA procedure SST, SSA and SSE, and then once the test is over and it is saying that there is difference, then go for different parameters, calculate all that parameter tau 1, tau 2, tau 3 or tau up to tau capital L, then compute the error also, and using Taki test or Bonferroni that confidence interval do this, also do the hypothesis testing for the parameters whether they are significant or not, whether the difference between the parameters values are significant or not. That is not sufficient, you have to do this adequacy test also. So, under adequacy test first point is normal probability plot. Now, come to the second point, independency. What we said? We said that the this observations, they will be independent to, there will be no correlation between one observation to another observation. So, that will be tested through, if you plot the residuals or the errors again, you are putting observation order. In this case our observation order is 1 2 like this 15, and you are writing here epsilon IL estimated the way it is estimated, you got, it is not arranged one, it is not arranged in ascending or descending order, it is the way your first observation is this, what is the value, second observation is this, what is the value. So, then first observation value will be 3.80, second one 1.20. So, like this if you go to the 15 one 2.40, this one you arranged for normal probability plotting, but here you do not require to arrange, and you see the slide here, So, these are the observation numbers, and this is basically the residual value, and if you plot, and you must not get any trend. Clear? So, we can say there is no serial correlation between one observation to another. Third one, what you have to test, that non-constant variance. We said that the variance is equal across the population. So, here what you require to do, you require to find out the fitted values and residual. Now, what are the fitted values here? What will be the fitted value? So, you see what we have written here, that epsilon I L is x I L minus A L bar. So, that means you have written like this, that x I L equal to A L bar plus epsilon I L. Fitted value means without error. So, that means I can say x I L fitted value is A L bar. So, as a result, what will happen, you will find out that for population 1, that is A1, for the first 5 values, it is replaced by the average. This is average across A1. Similarly, average across A2, second 5 values, third 5 values is average across A3. This is what are the fitted values, and then residuals already you have computed across everything. So, now you fit or plot against residuals to fitted value. Here, are you getting any difference in variability? I think this one, first one, little difference is there, because this is the mean value 71.80, and this across this mean the variability is little higher compared to the other two, but these two are almost equal. Okay. But we have tested this, you have to test through some statistics, that Bartlett's test I told you in earlier. So, here it is showing that the population 1, that means level 1 A1, variability is little more. It is apparently like this, but it may not be true, because this is basically a plot where the scale difference will make changes. So, I think there may not be the difference, but it should be tested. We have not tested in this example, but earlier example we have tested. So, if there is departure from equal variability, then it will be reflected in the fitted value versus residual plot. Okay. So, this is our one way ANOVA.
Sir, there is a difference, means this assumption that they are coming from the equal variability. So, can we use the ANOVA?
We can use there. You are saying that there is the violation of equality of variances. Yes, you can still use ANOVA. That ANOVA statistics or ANOVA procedure is robust procedure, but again what I can say, in that case what it is only advisable that you take equal sample size across the populations. Okay. If you do not take equal sample size, then there will be little problem, but you have to be very much
this assumption is very
vital assumption. Vital as well as complicated, because most of the times in the real life situation it is difficult to get normality. Normality you may get, but the equal variance part it is difficult. So, under such condition what I suggest that if possible you go for equal sample size and increase the sample size, and second is that other way you transform the variables. There are different types of transformation. For example, power transformation is there. If there is normality problem, then Box-Cox transformation is there. So, most of the time if it is not homogeneous, the normality assumptions also is violated. So, if it is homogeneous, and if it is normal, traditionally it can be, it is homogeneous also, that homoscedasticity part. Another thing is that you, before doing ANOVA, why can't you remove the outliers? Because the variability will be very much affected by the outliers. So, you remove the outliers. If you remove outlier, it may so happen that your variability component will be within the control. Okay. This way you please try, but again I am telling you, I have done 3-4 different analysis concerning the equality of variances, particularly in the multivariate domain. Very difficult, we are not getting equal covariance matrix. So, then I searched that what to do. There are many statistics which are basically robust against this type of problem. So, you have to search the appropriate statistics and use. Problem 2, two-way ANOVA. I think last class we discussed MANOVA, but before MANOVA I have given you some idea that when the two factors are governing the behavior of the system, then two independent factors or dependent factors. So, depending on the nature of the relationship between the factors, you may find out that the behavior of the system will be different. Now, here in the same example, but the data are hypothetical data. So, you may not get the exact one-to-one relationship between the department effects here in this problem with the problem given in 1, that may not be correct, but let us see that it is a separate problem now, that in order to evaluate the safety performance, as I told you, 3 departments and 3 age groups are considered. That means, what is our assumption here is that the 3 departments are 3 different type populations or levels, and different age groups also have different levels. That these are the different levels, they mean different population, that sense. So, henceforth, as there are 2 factors are coming, we will not use the word population frequently, we will use the word factors. So, department is one factor, that is A, and age is another factor, that is B. Now, department has the A factor has 3 levels, A1, A2 and A3, and B factor, which is the age factor, which is having also 3 levels in this example. So, that means we are saying A means department, B is the age. What do you want to say? We are trying to establish that, is it that there is difference across departments in the safety behavior? Is there difference between age groups? Is there interaction between age and department? Interactions between age and department, that is clearly written here. Do the departments differ in their safety behavior? That is our first question. Do the people in different age groups differ in their safety behavior? Are there interactions between the department and age groups in terms of safety behavior? Getting me? Now, if your query is only the first one and you do not consider that age is an important factor, then it is only one way ANOVA, what we have done earlier. As we are saying that it is not only the department is talking about the working condition, but the people behavior, people expertise, people that thinking, that is not coming under department. We want to capture this through different age groups. So, as safety is an issue of the unsafe acts and unsafe conditions point of view. So, first the department 1 we are treating it as unsafe condition point of view, and age factor we are considering at that individual influence point of view. Now, suppose 3 data points, equal sample sizes. So, it is again suggested that it is better you go for equal sample sizes whenever possible. So, here n equal to 3 and our 3 departments A1, A2 and A3 and 3 age groups B1, B2 and B3. Okay. So, here 3 data points 3 3. So, that means across A1 your data points 9 3 3 3, this also 9 3 3 3, this also 9. Similarly, across age group 1, age group 2, age group 3, 9 data points. So, that means this is my I n. If I say that with respect to this is 9, like this, some notation we can use here. Then the gross is the total capital N is your 27. This is the data as far as the number of observation point of view, this is the case, and you see that what are the different values. Suppose x, if you want to use the notation like this, for departments we will be using L, for age groups we will be using M, and for observations we will be using I. So, any observation here it can be denoted by X, I, L, M. Any observation can be denoted by X, I, L, M. So, if this is A1 B1, so X 1 1 1 is 68, X 1 1 2 is 65, X 1 1 3 is 73, like this. What we want? We want to first see that is there any effect of the departments, effect of the age groups and interaction effects. So, we will go by hypothesis testing. What is your hypothesis here in this example? My hypothesis is that from the department's point of view, if I say tau 1 equal to tau 2 equal to tau 3 equal to 0. I am not writing mu 1, mu all those things. Then this is from department point of view. Similarly, from suppose beta 1 equal to beta 2 equal to beta 3 equal to 0, that is from age point of view. Now, similarly, what will happen basically tau beta, I am writing now LM. L stands for the department, M stands for the age, that also will become 0. Now, that combination will be there, tau LM, all those things, this will be 0. So, why this is coming? This is coming because of the interaction point of view. If this is the case, then what are the sources of variation? First one is department, which is A, second one is age, which is B, third one is interaction, which is AB, fourth one is error, fifth one is that, this is the total one, this 4 sum is, this is the total. So, this is our sources of variations. So, what you require to compute? You require to compute SS. SS means sum square A, sum square B, sum square AB, sum square error, sum square total. So, how do you compute this? What will be your computation of SSA? You just see this table. It is not changing this one?
No, sir, it is coming.
Okay, no, I am saying that when okay, no problem. So, see that what is the total across A1? Total means 68 plus 65 plus 70, all values. This is 644. For A2 it is 695, for A3 it is 647. So, we are denoting it as A1, A2 and A3. So, write down A1 equal to 644, A2 equal to 695, A3 equal to 647. Similarly, you see across the column, when you make the total, you will be getting that column totals, which are basically for the different age group. So, you will be getting B1 equal to 631, B2 equal to 701 and B3 equal to 644. Okay. Another thing which is also equally important here, we want to see the interactions. So, the interaction, this each of the cell is the interaction part. Now, you are making the sum total of each of the cells, that is AB part. So, this one if I say sum A1 B1 is 203. So, if I write like this A1 B1 203, similarly A1 B2 218, these are all sum. So, you can see that 203, 218, 223, 215, 260, all those things are coming under the total across and the total in each cell. So, that we are denoting by ABLM. So, AB11, now AB12, AB13, like this. So, how many sums you are getting? One is the, if I say this is the marginal sum across department, this is marginal sum across department, this one is marginal sum across age group, and then these are basically joint sum. Joint sum mean basically these are the combination, each combination what is the sum value, and then you also require to compute the grand total. In this case our grand total is 1986. So, when you require to go for 2OA ANOVA, you will be getting a table which is known as contingency table. It's a contingency table looking. Okay. So, in the contingency table there are marginal counts across rows, across columns and joint counts. But here our values are not count value, our values are basically that continuous values, but you are getting values. So, we will not use the contingency table word, we will use that this is our data set. Now, you are calculating 4 things initially. One is across rows the total, across column the total, then across cells the total, and then the grand total. These things will be used to compute SST, SSA, SSB, all those things. This is our computational formulas from equal sample size point of view. You see, first what is the total observation? Total observation here in this example n equal to n L and into m, where our n is 3, L is 3 and m is 3. So, this is 27, and that you have seen earlier. Then second quantity what we are computing? We are computing the grand total G. So, that is going through all the cells. So, as a result it is I and all the values in each cell. So, I equal to 1 to n, this is talking about all the values in one cell, and L equal to 1 to L for the departments or A factors, m equal to 1 to B factors. This is the grand total. Now, grand total values we got, it is 1986. Now, AL 3 AL values you have already seen, that is 644, 695, 647. Then you got 3 values across age, that is BM, that is 631, 701, 644, and you have a large number of values because 9 values, because there are 3 cross 3 table. So, 9 values for joint A B jointly, what is happening, what are the values, that you will be getting the addition, some of these values you are getting. Okay. So, then what will be your SST calculation? SST calculation will be SST is 3 sum XILM this square minus G square by n. Okay. So, when you talk about SSA, SSA will be, you are considering only the rows. So, L equal to 1 to L, and that will be your x I, no, we have already created A L square by n m minus g square by n, because against each row you will be finding out that we are not considering the B factor effect. So, ultimately there are 3 cross 3 9 observations. So, here 9 observation, 3 cross 3 9 observation. So, what will be our SSB? SSB across m equal to 1 to capital M, then that is B m square by n will be there, but it is m is varying. So, L will be written here, and minus g square by capital N. Okay. Now, we will create another thing which is known as SS subtotal. SS subtotal, I think if you see that, I told you that 3 cross 3, here the sum of all values in this cell, sum of all values, sum of values, like this 9 values are there. So, these 9 values will be coming from L equal to 1 to capital L and M equal to 1 to capital M, where capital L equal to 3, capital M equal to 3, here everywhere this is also 3. So, that 9 values, some values, these values we have given a name A B L M. You have seen earlier this value I have given this name. So, this square, and it is basically addition of 3 values. So, divided by n, that equal to 3 minus g square by n. You want to see this, I am showing this one. You see what is, we will explain with respect to this. So, what we are saying that SST, first one is SST 68, 65, 70, all values you square them and add, minus this g square by capital N. This is this formula. All values in the table, these are squared and then added, then minus this. Now, for the second SSA, you see what we have taken? We have taken the sum across the rows 644, 695, 647, and these values you are squaring first, then dividing it by that here 3 plus 3 plus 3 9 values are there. So, it is the second one. So, n m divided by n m. So, similarly, you will be doing this for across column. Just see across column 631, 701, 644. Okay. Now, subtotal means this is subtotal 203 ABLM 203, 218, 223, 215 like this. So, you are squaring these all, then you are making total, then dividing it by this the number of observations and then following like this. So, you will be getting subtotal, but once you get subtotal, you are in a position to calculate the interactions parameter SSAB. Okay. SSAB will be SS subtotal minus SSA minus SSB. Okay. In this way you can write, or the way we have written first, SSAB equal to SS subtotal minus SSA minus SSB. So, what are the items you have now? You have SST, you have SSA, you have SSB, you have SS subtotal, and you have SSAB. What is required to be calculated now? SSE. SSE will be SST minus SSA minus SSB minus AB. Because you see the total is SSA, SSB, SSAB, SSE, SST. So, SSE will be SST minus this, minus this, minus this. So, this is the calculation part, decomposition of total sum square into individual sum squares. Those individual are the sources, and we have computed this. Based on the computation, you got the values like this: SSA equal to 175.63, SSB 279.63, SSC 220.37, SSE 350.67 and SST 1026.30. These are the SS values. Now, what will be your degrees of freedom here? What is the total observation? 27. So, 27 minus 1, that is 26. How many levels for A? 3. So, 3 minus 1, 2. How many levels for B? 3. 3 minus 1, 2. What will be the AB case? 3 minus 1 into 3 minus 1. That means, AB's case, here A has L minus 1 degree of freedom, B has M minus 1 degree of freedom, the multiplication. So, 2 cross 2 equal to 4. The rest 26 minus 4 minus 2 minus 2, that means minus 26 minus 8, that is 18 is the error degree of freedom. Okay. Now, what will be your MS then? MS will be 175 by 2, that is 87.82. 279.63 by 2, that is 139.82, then 220.37 by 4, this will be 55.09, 350.67 divided by 18, this is your 19.48. Okay. Then what you require to know? You require to know F values. Your FA will be MSA by MSE. So, 87.82 by 19.48. This value will be 18 in 4.51. Then FB 139.82 by 19.48. This value is 7.18. Then FAB, which is 55.09 by 19.48, which is our 2.83. So, your ANOVA table is ready. What you require now? You require to find out tabulated value, let some value, alpha value you take 0.05, all those things. Now, see this, we have identified what is the p value for f equal to 4.57 with degrees of freedom 2 and 18. This is 0.026, it is less than 0.05. Second one is also less than 0.05, but third one is not less than 0.05. So, if you consider alpha equal to 0.05, that means 95% confidence or 0.05% significance level, then your A and B effect are significant, whereas interaction effects are not significant. But this value is very close to 0.05. 0.056 is very close to 0.05. So, what I mean to say then, that means you can consider it also significant. So, the result is there are differences across department and age groups, interaction is significant at the probability level. So, we can say also interaction effect is there. Now, once this test is over, now what is your next? You have to estimate the parameters. These are the formulas for estimation of parameter. You see here again we are partitioning the observation in the ILM observation, mu plus mu L minus mu, this is the A effect, mu M minus mu, that is the B effect, then mu Lm minus mu L minus mu m plus mu. This one is your, you see that you have taken here mu L, so you are subtracting mu L, here mu minus mu plus mu, this mu plus, so it is cancelling. Finally, xil m minus mu Lm, because one mu Lm is added here, and this is the partition. So, this first one is grand mean, second one is A effect, third one is B effect, fourth one is AB, that is interaction effect, last one is error. So, this one we are writing in the same manner. So, grand mean G by N. Now, A effect, that AL bar, AL by NM, BM bar, BM by capital NL, then AB bar LM, that is AB LM by small n, then mu is nothing but G bar, mu L is nothing but AL bar, mu M is nothing but BM bar, mu LM is nothing but AB LM bar. Then tau L will be that mu L minus mu L cap minus mu cap is the tau L cap. So, that is AL bar minus G bar. So, similarly, beta M you are also calculating, similarly the interaction effects you are calculating. Okay. And then what will be the predicted value of each observations? This will be except the EIL component. So, see this component is not there. Now, if when we do manipulate this one, what you will find out? You will find out that this one is nothing but AB bar LM. This is the joint, that cell average are the predicted values. Getting me? So, you see that this calculation we have done like this. So, this is our 71.56, this AL bar. If you subtract this minus this, you will be getting the tau 1, 77.22 minus this tau 2, 71.89 minus this tau 3. Similarly, beta 1, beta 2, beta 3. Similarly, you will be getting tau beta 1 1, tau beta 1 2, tau beta 1 3. That means 67.67 minus this. This way you will be able to get. Now, see what is happening. You are getting everywhere the tau L, BM and tau BL. These are the parameters. Apart from this, what more you want? You want to calculate the error component also. Error component is also your parameter. Okay. I think we will start again. We will start again, and this is okay. Thank you very much.